Good morning, everyone. I'll be taking a presentation about column connections and column beams. Now, let us proceed. Glazings and battenings. Glazings and battenings are specified in IS 800 in page number 50. If the load is about 2000 kN, we have to go for a built-up section. It may be two height sections or two channel sections. Lacings are preferred when a column gets eccentric loading. Eccentric loading is nothing but the loading is about a distance from the CA, that is like a channel section connected at columns. Battens are used when the concentric loads are applied on the CG, that is trusses in stations. This is the shows the different types of lacings. There are four types of lacings: single lacing, double lacing with cross members, which is not recommended and which is not used regularly, and single angle lacing with gusset plates. Now these are the examples of lacings. You can see that lacings have been used as shadows, that is the lacings which is given at one side is the same as that on the other side. In the next picture, the second picture, you can see that the plates, gusset plates given as attachment to the lacings. Now this is the example of battens. Battens are horizontal members which are kept at a distance. Types of built-up compression members are laces plus battens. You can see that the columns are named as cords and the members are named as battens and lacings respectively. The distance between two battens is known as the module. Now this is the column bases. Column bases are used in places where the steel load is more compared to the concrete load. There are many types of gusset plate and column based fixations, and this can be seen over here. The first is a normal column based fixation. The second is a base plate with gusset plate and extra cover plate. The third is the angular column plate fixation with stiffeners, and the fourth is a column base plate arrangement with stiffness applied onto it. Now we'll see that if load is about 2000 kN, we have to go for a built-up column. It may be a 2 eye section or 2 channel section or 2 angle sections for 4 angle sections, and hence they must be tied up together. This will help the lacings and this can be helped using the lacing and batting. The tying up is not just for making them held together, but also it helps to stiffen the member against local buckling. If lacing plates or bars are placed, they must be placed in shadows. As I have told in the previous slides, in this picture you can see that the lacings are similar at both the sides. The lacing should be continuous from top to bottom. The width of the lacing plates should not be less than 3 times the normal diameter of the bolts or rivets. The thickness of lacing plates shall not be less than 1/40th of the effective length of lacings in case of single lace system, and in case of double lace system it shall not be 1/60th of the effective length of lacing. The effective length of lacing is the distance between the inner to inner bolts and the end connection in case of single lacing. That is, if the bolts are given at the ends like this, then the distance between my two thumbs is referred to the inner to inner distance of the effective length of the lacing system. In case of double lacing system, it is considered as 0.7 times the distance between inner bolts. In case of welded sections, it is 0.7 times the inner welds. The inclination of lacings is restricted to 40 to 70 degrees. This restricts the spacing of lacing shall be such that the local slenderness ratio should not exceed 50 or 0.7 times total slenderness ratio of the columns, whichever is less. But if two channels are kept back to back with close spacing, the spacing of lacing should be such that the local slenderness ratio should not exceed 40 or 0.6 times the total slenderness ratio of column, whichever is lesser. Traverse load, that is the horizontal load acting on the lacing system, should not be less than 2.5% of the column load. In case of lacing system, the effective length of the column shall be increased by 5% to take care of the shear deformation. But in case of battens, it is 10% excess. If two members are kept close, then the IYY must be greater than IXS. That is, the moment of inertia about an axis perpendicular to lacing plane YY must be more or equal to inertia about an axis parallel to the lacing plane, that is XX. Generally, lacings are preferred in case of eccentric load and battenings are preferred in case of concentric load. The lacing plates shall be designed as a compression member, but center ratio is restricted to 145. A lacing plate mustn't be checked for tension member. If battening system are available, then the minimum number of bays shall be 3. The minimum number of bays shall be 3. That means there must be a bottom batten and the top batten, and in between 2 battens. So 1 bay, 2 bay, 3 bay. So number of bays should be 3. The column bases, as explained earlier, column bases are held as if placed directly, the steel column punches the concrete. This can be showed using an example. Like if this is a loaded punch, it punches the column and disintegrates the whole section. But whereas if a column plate is kept over here like this, the column base is hits on the section and the total load is distributed throughout this base plate and then distributed onto the concrete. The concrete can only tolerate about a strength of 0.45 FCK. Hence, it disintegrates the concrete, leading to failure. Using base plate below the steel column to distribute the load. Thickness of base plate or the base slab is mentioned in IS 800, page 47 and 84. This is how a normal steel compound column is designed as per IS 800. This is not the we can see that 1000 kN of loading is used. Hence, let us go for a combined column. We can see that ISHB 350 is used and 2 ISHB used. The distance is between the center to center distance of 2 webs is taken as S. The RXS and IXX and IYY are all got from the code book. For the new built-up column, the IXS and IYY are simulated from the following formula. 2 into IXS of the value given from the code is equal to 2 into I plus AH square. Here the H is nothing but S by 2. Hence, substituting and equating, we get S value as 140 mm. We know that lambda is equal to L by R, where L is the L effective length. So effective length is 16 meters and R, the radius of line is 149.3. Equating it, we get the lambda value, which is 107.6, which is less than 180. Hence, the section is safe. Now, the column is built up. So as per table 5.1 on page 39, we have to go and hence we get the value of 75 megapascal. Now we have to find the stress in the column. The stress in the column is force by area. We know the force as 1000 kilonewton that is provided, and the area using the code book steel table we can find out. Hence, the force by area is 58.2, which is very much less than the 75 megapascal provided. Hence, it is safe. Now, these two I sections has to be connected. Hence, we will go for a lacing system. This is a lacing system where theta is restricted between 40 and 70 degree. Let us go for 45 degree. Here, the C by R over must be less than 50 degree as told in the code book, and 0.7 lambda of the column, the local lambda. Now we go to find the distance between both the I sections, that is the lacing bars, the inner to inner distance of the lacing bars, the effective length of the lacing bars, that is 2s minus 125. 125 is the length of the flange section. Hence, calculating we get the D as 155. Since it is angular, it is D into sin 45 or cos 45. We'll get the value of the length of the lacing, that is D root 2. Sin 45 is root 2. Hence, D into sin 45 is D root 2, and we'll be getting the value that is 219.2 mm. That is the length, effective length of the lacing. Now, the minimum required thickness of the lacing system is L by 40 as told in IS 800. As we will be going for single lace system, we will go for the value is L by 40. If you have gone for double lace system, the value gets increased to to L by 60. So let us provide a 8 mm thick lacing. Now check for traverse load. We have mentioned that the traverse load must not be more than 2.5%. Hence 2.5 into the given load, we get 25 kN as a traverse load. So F into sin 45. Sin 45 is used for vertical loads. F into sin 45 into 2, because 2 lacings are used, is equal to 12.5 kN. So the total F is equal to 8.84 kN. The given 25 kN is for single column, for both columns. Hence for single column is 25 by 2, that's 12.5 kN. Now we know that I is equal to R square into A. Now R is equal to root of I by A. Solving it, we get I is equal to BD cube by 12, and substituting the values, and A is equal to 75 into 8, that is, we get the value of 2.31 mm. Now again, lambda is equal to length L by R. L effective is D root 2, which has calculated already, and R minimum is taken. Hence, we find out the value as 94.89, which is lesser than the given value of 145 for lacings. Hence, the section is okay. Now, as per IS 800, we can say that the built-up section comes under the buckling class C. Checking the value of lambda onto the table 5.1, we get the answer as 85.21 megapascal. This section maximum capacity 85.21 megapascal. Now let us consider our given column. For our given column, F by A value is 8.84 into 10 power 3. That is the force we have found out earlier, divided by the area of single lacing bar, that is 14.73, which is very much lesser than the given column. Hence our column is safe and the built-up section is withstand any pressure. Now check on axial tension. Now let us provide a rivet section. Now gross diameter of the rivet is 20, and the diameter of extra diameter, that is the whole diameter, is 1.5. So 21.5 is provided. Now the net sectional area is total length minus the bolt size into the thickness of the plate, that is 75 minus 21.5 into 8, which is 428 mm square. Now the tensile strength on the lacing bar is force by area. 8.84 in 10 power 3, that's found out, and area net is what we calculate now. Hence we get a value of 20 into 6.5 Newton per mm square, which is less than the 150 Newton per mm square. Hence it's safe. Now thickness of flange and thickness of lacing is found out. Rivet value of 20 mm diameter, we get V is equal to tau AB pi by 4 into 5 square, which is 100 by 1000 into pi by 4 into 21.5 the whole square, and we get the value of 36.3 kN. Thus the rivet value is taken the least of both the above, that is 36.3 kN. The number of rivets required is the force by number of rivet value, that is 8.84 by 3.63, which is 0.24. Since the number of rivets has to be provided as 2, let us go for 2 rivets on each side, and hence we have completed the design of the section. Thank you.